Welcome to Chapter 4, the last chapter of quantitative reasoning. Hang in there, folks. You're almost done. You can crush this course. So in Section 4.1, we're going to look at just the key terminology and probability, and then we're going to compute theoretical probabilities, and then we're going to ignore all the rest. So this is just going to give you a basic introduction to what is probability. So really what probability is a numerical representation of how likely something is to occur. You can think of it as a percent chance, you can think of it as a number between 0 and 1, you can think of it as a fraction. So when a forecaster says there's a 70% chance of rain today, that is the probability that it will rain. 70% chance. Since it's above 50, it's more likely to rain than not rain. So one of the big things we work with in the probability world is what's called a sample space. So there's things like flipping coins and rolling die and drawing cards. These are all called probability experiments. And in general, a probability experiment is a process that leads to well-defined results, which we often call outcomes. So an outcome is the result of a single trial of that experiment. And then what we want to do is define the sample space of that probability experiment. So let's look at these two examples. The first one here says, we toss a coin. How many possible outcomes are there? Well, if you think about a coin, there's either heads or tails, meaning there are a total of 2 possible outcomes. When we list this as a sample space, we often use brackets to denote a set, and then we'll use like symbols to represent heads and tails. So H for heads and T for tails. Another one, if we roll a single, and we should insert here 6-sided die because there's all different number sides of die. How many possible outcomes are there? Well, for that one, there are 6 outcomes. And if we were to list them, which is exactly what we're going to do, this is the list of all 6 outcomes. Note I'm using the squiggly brackets. This is the set of all possible values in this probability experiment. So our goal then is to predict what are the possible, what could happen. So one of the things we have to do is, just as we said, list the sample space, and then we can calculate what's the chance when we roll the die that it lands on a 1, assuming each of the outcomes are equally likely. So here's a bunch of different experiments. We already did these first 2. Let's look at the second one, answer a true and false question. Well, that's essentially the same thing as flipping a coin. If you're randomly guessing it, the sample space is either true or false. Now, the second one gets a little wilder. If we flip 2 coins, the experiment is the 2 outcomes that the 2 coins land on. So we could have that both coins land on heads. We would denote that heads, heads. Another outcome could be one of them is heads and one of them is tails. So here the first one is heads, the second one is tails. Or the first one could be tails and the second one could be heads. And finally, they could both be tails. So these are all the possible outcomes of flipping 2 coins. So we're going to skip the next page because I think our author gets a little wild with the notion of event and outcome. And we're going to jump all the way to page 302. So we're defining that these things are called theoretical probabilities, and if you take 133 here at Jackson College, we often call these classical probabilities. It's when the experiment we're doing is based on a theoretical set of things like a deck of cards or rolling dice, or we could say picking items from a mixture of like marbles out of a jar that are different colors, where we know all of the possible outcomes. We can list them all out. So from the outset, we know what can happen, and then we can try to predict what would happen by calculating the probabilities. So question 11 says, you'd have to be awfully bored to flip a coin 100 times, but what if you did? About how many times do you think it would land tail sides up? Well, if we assume that each outcome is equally likely, we would say that the probability it lands on tails is about 50%, or 50 out of 100. Now, in reality, if you actually do that, it may not be exactly 50 out of 100, but it's going to be really close. So what percent of the time would we expect that to happen? Well, that's the same thing as this. It would be about 50%. And then we could write that as a fraction. Oops, I already did that. Oh, I was supposed to say an 11. 50 times it would land on tails. So that is a theoretical probability, that 50% chance, or that 50 out of 100, that that coin could land on tails. In general, when we're calculating the probability, a theoretical probability, we look at the number of ways an event can occur, so flipping tails, out of the total number of ways that we run the event. So let's look at this particular one here. We're going to roll a 6-sided die, and we want to find the probability that the die lands on 2. Now, be careful. I often see students who want to write this as 2 out of 6 because they see the number 2 and they want to use that. What you want to think about is, here's our sample space for the dice. 1, 2, 3, 4, 5, 6. How many of these outcomes are the number 2? And that may seem like an obvious answer, and if that is, good. There's only one outcome that is a 2. So the probability of rolling a 2 is 1 out of, well, how many numbers are there? How many possible outcomes are in this sample space? There's 6. So it's a 1 in 6 chance that the dice lands on a 2. We could represent that as a decimal if we wanted to. Often I think that might be an easier way to understand it. That's approximately 0.17. We could also turn that into a percent and say there's a 17% chance that the die would land on a 2. Continuing with the same sample space, we're now asking, what's the probability that we roll a number less than 5? Well, looking at our sample space, here's all the numbers that are less than 5. 1, 2, 3, 4. Note there are 4 options that are less than 5, so there's a 4 out of 6 chance that you roll a number less than 5. And those particular outcomes are 1, 2, 3, 4. If you want to, you could simplify this fraction. You could write this as 2/3. I think Connect Math is actually going to require you to do that. Just look for the directions and how they say that. You might also need to convert this to a decimal, round it to 2 decimal places, or you may need to write it as a percent. Okay, let's do another one. How about rolling an odd number? So odd numbers are numbers that are not divisible by 2 and result in a whole number. So looking at our sample space again, here's the odd numbers, 1, 3, and 5. Notice there are 3 odd numbers in our sample space of 6 possible outcomes. So we would write this as 3 divided by 6, which is also equal to 1/2, which is equal to 0.5, or 50%. Now, notice if you're questioning what's with the squiggly lines, that's because I rounded these numbers. And why do I not have a squiggly here? It's because these are exactly the same. All right, one more. This one is a little more involved. So if 3 coins are flipped, we want to write the sample space. And to do this, we're going to use an H for heads and a T for tails. So this gets a little wild. The first option, I'm going to start with just listing the first thing as heads. So the first coin could be heads, the second coin could be heads, and the third coin could be heads. Then we could have heads, heads, tails. We could have heads, tails, heads, and we could have tails, heads, heads. So there's our first set of options. Now I'm going to do all tails, 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 and then run through the possibilities of the different ones being heads. So we could do tails, 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 and then we could have tails, tails, heads. We could have tails, heads, tails, or we could have heads, tails, tails. And this turns out to be the exact sample space. You could write it in a variety of different orders. You just have to make sure there's exactly 8 options. Let's count that real quick to make sure I did it right. 1, 2, 3, 4, 5, 6, 7, 8. So that's the sample space. And now we're going to do some calculations. Well, what's the probability we get 2 tails? Well, let's find all of the outcomes in this sample space that have two tails in them. Here's one with two tails. Here's one with two tails. Here's one with two tails. So this has three tails. That doesn't count. These all have one tails. Those don't count. This one has no tails. So this probability is 3 out of 8. As a decimal, that is approximately, no, that's exactly 0.375. And as a percent, that's 37.5%. All right. What if we want at least one of these values to have tails? Well, at least one means one or more. So if we look at our options here, all of these have one tails in them. There's only one that doesn't. So for number 19, we're looking at that to be 7 out of 8. And 7 divided by 8 as a decimal is 0.875, and as a percent, it's 87.5%. Last one, how about what does at most one tail mean? That means you can have one tail or zero tails. So the most amount of tails you can have is 1. That corresponds to this set, this one, and this one. So that was 1, 2, 3, 4 options. So that would give us a 4 out of 8, which is a 0.5, which is 50%.